As we've seen so far in our study of chemical kinetics, we can create phenomenological rate laws that tell us something about the time behavior of a reaction, in particular how fast it can occur. But we've also seen that while we can go from differential rate laws to integrated rate laws, this becomes more complicated if the rate law depends on more than one reactant. And in particular, we can begin to associate these different reactions with a molecularity. And by what I mean by molecularity is how many molecules or how many species are involved in the phenomenological rate law. So for example, many of the things that we've been studying really are unimolecular processes. That is, we have one reactant that goes to products, and with this one reactant we can then write down a rate law that is, somehow related to the change with respect to time of that reactant, and it might be equal to a rate constant times its concentration raised to some power. All right, so this is a fairly simple arrangement, and it gives us rate laws that we can readily integrate. But we've also seen that when we have a process, even as simple as a bimolecular process, which might involve A plus B going to products, if the differential rate law depends on both A and B, we get a more complicated expression. And I won't reproduce that here, but I hope you recall from the end of the last video that we got a fairly interesting expression out of that, but not one that was very intuitive. Now we can also have higher order processes, so I'll add termolecular to this list, which would be something like A plus B plus C going to products. And I think it's easy to see that as we go down this list, we're getting more and more complex in our treatment of reactions. That is to say, these reactions are we're less and less capable of writing down explicit expressions for their rate laws. Now, one thing that will be true throughout, though, is that we can associate the rate with the rate of disappearance of reactants. So, for example, something like this, and it could be for any of the reactants if we now divide by their stoichiometric coefficient. So, in general, we would have something that looks like this. These two expressions are equivalent, and so we can associate them consistently with a rate. We could also extend this to products. For example, if C were a product, it would be the positive derivative of C with respect to T divided by its stoichiometric coefficient. So this gives us a consistent definition for the rate. And with this consistent definition, we can begin to anchor our whole study of the rate of chemical reactions. Now, when we do this, there are several things that we don't know at the beginning of analysis of an equation. We do not know the value of this rate constant K, and we do not know necessarily the order of the reaction. Okay, when we have a whole series of reactants like this, each one of them can have their own order, individual order, and it's only the sum of those orders that gives us the total order of the reaction. So in general, when we do experiments to find these things out, what do they measure? All right, typically experiments measure the time behavior of a reactant. So for example, the time behavior of A, and I'm always going to denote that with a little subscript T to tell you that that's the concentration of A corresponding to time T. Okay, if I put a 0 there, that's the concentration of A at time 0, which would be the initial concentration. So these experiments are measuring how A evolves in time, beginning with initial concentrations that are specified. So those could be the initial concentration of A, the initial concentration of B, and so forth, depending on however many reactants we happen to have in the reaction. All right, now how do we translate this into a rate law? Well, if we're measuring this, I'll point out that if it's a unimolecular reaction, this basically just gives us the integrated rate law. That is to say, it tells us the time evolution of A as a function of time, which is equivalent to the integrated rate law. Now, it doesn't give us a mathematical expression for that, but it does show us how this behaves in time. But when we don't have a unimolecular reaction, it's a little bit more difficult. And it will turn out that it's actually more useful for us to think in terms of the differential rate law. But Differential rate law is, or the rate is not something we can measure directly. So I'll just say rate is something difficult to measure directly. So how do we get around this? Well, if we can measure A at a time t, we can also measure A at a time t plus delta t. And if I put these two together and I make delta t small enough, I could actually calculate a quantity that would look something like this. I'd have A at t plus delta t minus the concentration of A at time t, and then divide this by that interval of time, and this is in effect equivalent or roughly equal to this time derivative of the concentration of A with respect to time. So this is in fact how we would go about measuring these things experimentally. We would measure the concentration at different time points and then divide by the time interval between those points to get a slope or a rate for that. Now, we know that at the end of this, we're going to relate this time derivative in a differential rate law to a general expression that looks something like this. It's going to be A raised to its power, B raised to its order, and so forth. Or we could write this more generally, and I hope you'll allow me the carte blanche to use more mathematical notation. If we're doing this over all the possible reactants, it would be each individual reactant raised to its order in the reaction. Remember that these orders are not the same as the stoichiometric coefficients for the chemical equations. And we may talk a little bit about that in a subsequent video. But the general rule is that we're going to have more than one, if it's a reaction that involves more than one reactant, we're going to have more than one reactant involved in this general rate law. And it's going to be, in general, difficult to figure out an integrated rate law for that result. So we're going to really care more maybe about the differential rate laws moving forward. Now I'll remind you that the total order of this reaction is just going to be the sum over all of these numbers. So the total order would be the sum over alpha of these exponents n sub alpha. Now how are we going to proceed with this? Okay, I'm trying to give you a general outline so that you'll understand sort of what it is we're doing in the subsequent videos. But what I'll say is that in general what we want to do is we want to measure something where we have the maximum amount of information available at the beginning, and what we're measuring is maybe just one parameter. Now I've mentioned already that we're mostly measuring the time dependence of the concentration of a reactant. Now, if we're talking about having maximum information at the beginning, most times that means we're going to be focusing on the beginning of a reaction. So when we do that, it means that we can have the initial concentrations of all of the various species, as I've indicated up here. All right. If we know those, that's more information that we have at the beginning and less that we have to deduce from some measurement experimentally. Now, what we'll find is that when we look at unimolecular reactions, we don't always know if it's a unimolecular reaction off the top of, when we start, but if we're looking at a unimolecular reaction, we're going to be able to do a direct comparison to an integrated rate law. It is the only case in which we can do that. Okay, when it's not a unimolecular reaction, then we have to really fall back on the differential rate law. So I'll say bimolecular and higher. We're going to be looking at the differential rate law and using it to determine not only the order of the reaction, but also the rate constant. And we can get that information actually from both of these general methods. So both of these methods, a direct comparison to integrated rate law and the differential rate law, can tell us what the order of the reaction is, and we can ultimately use experimental information to get the rate constant. But one is going to be most useful for unimolecular reactions and the other more useful for the more general complex case.